Ladies and gentlemen, the National Science and Technology Laureates. Ladies and gentlemen, the President of the United States.
Thank you all. Thank you all very much. Please be seated. Welcome to the White House. I'm pleased to be in such distinguished company here in the East Room. I want to congratulate our honorees, and I want to welcome your families and friends. Each year, our nation honors outstanding work in science and technology. These honorees have given exceptional service in their fields. They bring great credit to themselves and credit to our country. Today, we express America's pride in their achievement and our respect for these national laureates of science and technology. I want to thank Sam Bodman, who's the Deputy Secretary of the Department of Commerce, for joining us. I want to thank Phil Bond, who's the Undersecretary of Technology for the Department of Commerce. I want to thank the Director of the Office of Science and Technology Policy for the President, Dr. John Marburger, for being here. Arden Bennett is the Director of the National Institute of Standards and Technology. Thank you, sir. Rita Caldwell is the Director of the National Science Foundation. John Bordonia is the Deputy Director of the National Science Foundation. Thank you all for coming. I want to thank the panelists who selected this outstanding group of laureates for their hard work. We've got two members of the United States Senate with us today, members from the mighty Delaware delegation. Joe Biden and Tom Carper, welcome. Thank you all for coming. Appreciate you being here. We got students from Benjamin Banneker High School with us today. I found it very interesting and wise that the students met one-on-one with each of the laureates to help develop their interest in science. Thank you for not only being scholars and pioneers, but teachers as well. The National Medal of Science honors pioneering scientific research that has enhanced our basic understanding of life and the world around us. The National Medal of Technology recognizes the achievements of men and women who embody the spirit of American innovation and have enhanced the nation's global competitiveness. Both these medals are authorized by acts of Congress and are the highest honors the President can bestow for attainment in science and technology. The men and women we honor today probably didn't begin their careers with the expectation of receiving such honors. Most great achievers in the fields of science and technology have a sense of calling. They're drawn to the work by their curiosity and by their talent. They carry out their work with patient effort and the openness to truth that leads to discovery. The highest reward for their work is the good they do and the knowledge they leave behind. The medals we confer today are a way of expressing our own gratitude to some of the most gifted and visionary men and women in America. The men and women are helping to enhance the nation's health and economic prosperity. They made their contributions to progress in a variety of fields, from physics to genetics to mathematical theory to engineering to the development of semiconductors. Some of them have made achievements beyond their own fields of endeavor, thereby showing the great potential of interdisciplinary research. Each of these recipients has set a standard of excellence. Each is widely admired by peers and sets a fine example for the next generation of scientists, mathematicians, and engineers. And all of them represent the finest qualities of their professions and the finest qualities of our country. This great nation provides opportunities and institutions that make achievement possible. We've got a vibrant free enterprise system. We've got the world's finest universities and generous support for scientific and technological endeavor. Yet all the great achievements we honor today are the sum of individual effort. And when we speak of American creativity and American ingenuity, we're speaking of men and women like our national laureates of science and technology. They have freely accepted the toil of overcoming challenges. They have put their considerable gifts to good purpose. Their fellow Americans are grateful to them. All humanity is in your debt. And now I ask the military aide to read the citations. It's my honor to present the medals to the national laureates of science and technology.
Leo L. Baranek. The 2002 National Medal of Science to Leo L. Baranek for his leadership, dedication, and contributions to the art and science of acoustics, for co-founding one of the world's foremost acoustical research and consulting firms, and for sustained contributions to scientific societies and civic organizations. John I. Brauman. The 2002 National Medal of Science to John I. Brauman for his contributions in chemistry, giving new insight into the properties of ions and the dynamics and mechanisms of reactions, and for his landmark achievement in clarifying the key role of solvents in determining acid-base chemistry. James E. Darnell. The 2002 National Medal of Science to James E. Darnell for his seminal scientific discoveries related to gene expression in animal cells, including pathways of RNA processing and signal transduction from the cell surface to genes in the nucleus, and for his contributions as a scientific educator. Richard L. Garwin. The 2002 National Medal of Science to Richard L. Garwin in recognition of his research and discoveries in physics and related fields, and of his long-standing service to the nation by providing valuable scientific advice on important questions of national security over half a century. James G. Glim. The 2002 National Medal of Science to James G. Glim for his original approaches and creative contributions to an array of disciplines in mathematical analysis and mathematical physics, which are fundamental to the theory of operator algebras, shockwave theory, advanced quantum field theory, quantum statistical mechanics, applied mathematics, and scientific computation. W. Jason Morgan. The 2002 National Medal of Science to W. Jason Morgan for his development of the theories of plate tectonics and deep mantle plumes, which revolutionized our understanding of geological forces that control the Earth's crust and deep interior, and consequently influence the evolution of the Earth's life and climate. Evelyn M. Witkin. The 2002 National Medal of Science to Evelyn M. Witkin for her insightful and pioneering investigations on the genetics of DNA mutagenesis and DNA repair that have increased our understanding of processes as varied as evolution and the development of cancer. Edward Witten. The 2002 National Medal of Science to Edward Witten for his leadership in a broad range of topics in mathematics and theoretical physics, including attempts to understand the fundamental forces of nature through string theory, and his inspired use of insights from physics to unify apparently disparate areas of mathematics. Calvin H. Carter, Jr. The 2002 National Medal of Technology to Calvin H. Carter, Jr. for his exceptional contributions to the development of silicon carbide wafers, leading to new industries in wide bandgap semiconductors and enabling other new industries in efficient blue, green, and white light, full-color displays, high-powered, solid-state microwave amplifiers, more efficient, compact power supplies, higher efficiency power distribution, transmission systems, and gemstones. Heron S. Gandhi. The 2002 National Medal of Technology to Heron S. Gandhi for his research, development, and commercialization of automotive exhaust catalyst technology, shaping the industry from its very beginning and continually pushing to improve the quality of the air we breathe. Also for leading the automotive industry in ensuring the judicious use of precious metals, including conservation measures such as recycling of spent converters and technological advances in precious metal utilization. Carver A. Mead. The 2002 National Medal of Technology to Carver A. Mead for his pioneering contributions to microelectronics that include spearheading the development of tools and techniques for modern integrated circuit design, laying the foundation for fabless semiconductor companies, catalyzing the electronic design automation field, training generations of engineers that have made the United States the world leader in microelectronics technology, and founding more than 20 companies. John J. Mooney and Carl D. Keith. The 2002 National Medal of Technology to John J. Mooney and Carl D. Keith for the invention, application to automobiles, and commercialization of the three-way catalytic converter. Through their persistent efforts, this technology is the key emission control component in all new light-duty vehicles in the United States and throughout the world. Nick Holonyak, Jr., M. George Crawford, and Russell Dean Dupuy. The 2002 National Medal of Technology to Nick Holonyak, Jr., M. George Crawford, and Russell Dean Dupuy for contributions to the development and commercialization of light-emitting diode technology with applications to digital displays, consumer electronics, automotive lighting, traffic signals, and general illumination. Charles Holliday. The 2002 National Medal of Technology to DuPont for policy and technology leadership in the phase-out and replacement of chlorofluorocarbons.
Thank you all very much for coming.
Winning the National Medal of Technology creates excitement, enthusiasm across the 80,000 men and women that serve the DuPont company today. The reduction of CFCs, in fact, the ultimate elimination of CFCs, was a major decision for our company to take. And when the scientific data said there was a harm to the environment, DuPont was the first to commit to a date certain to eliminate use of that chemical and also find replacements. This is a very important role model for how the world can deal with environmental problems. And I hope we will keep going back to that. But it took technology. So the awarding of this medal is very appropriate to support this. We truly believe science can play an important role in lifting the standard of living of not only the 2 billion people in the more developed countries we serve today, but the 4 billion people in the less developed countries. We're pleased as a company to be expanding our initial roots in chemistry into biology. We hope as a company we can pull together chemistry like we demonstrated here along with biology and solve some of the world's most challenging problems.
Before 1970, a soupy mix caused by auto exhaust draped over our cities. It would take an act of Congress and the invention of 2 men to change that. Carl Keith and John Mooney invented the 3-way catalytic converter, a compact metal container with catalyst inside to dramatically reduce automotive emissions.
Concerning the existence of the catalytic converter, people have heard of it, but they don't see it. It sits right underneath the passenger seat. It does its job without getting in the way of any other functions that are done with automobiles.
This job achieved the 90% reduction of hydrocarbons, carbon monoxide, and the more difficult nitrogen oxide as required by the Clean Air Act. With additional technological advancements, today Mooney and Keith's three-way converter has been universally adopted by every car manufacturer in the world.
In the beginning, our partner in development was Volvo and Robert Bosch. It's a great satisfaction to me to know that it's successful. It was instrumental in getting rid of lead. And lead is a poison, so that when I think of my accomplishment, always I think of that. It's also removed the billions of tons of pollutants that otherwise would be in the air. Brings a smile to my face at night when I go to sleep.
We drove back then in Bombay a full-size sedan, a beautiful Mercury V8. And never that I had dreamt that I will be spending most of my working life with Ford Motor Company.
Haran Gandhi has realized his dream with a 37-year career at Ford's research laboratory, where he applied his curiosity and talents to the complexity of an automobile's exhaust system. Gandhi pioneered the key technology needed for the new three-way catalytic converter. Gandhi designed the essential materials in catalysts needed for the converter to work. Research into the material design revealed another environmental conundrum. Only precious metals would be effective.
So we made an absolute rule that we will conserve, to start with, how much precious metals we need to make the catalyst, and we will also ensure that every catalyst on road recycles back, so that those precious metals come back for future use.
His colleagues describe Haran Gandhi as someone who will take an idea beyond the laboratory and into commercial production, with vision, persistence, conviction, and resourcefulness.
I thought chemistry shaped the life, and it touched upon everything we do in one way or other. So it excited me. At the same time, I thought the work in emissions area will help improve the air quality we breathe, and I will impact, one way or other, the lives of millions of people around the world.
When you look at the planet and people, and you want to build something that people see, I wanted to work where you can see, where a human can see.
Nick Holonyak, George Crawford, and Russell Dupuy each played essential roles in the development of light-emitting diode, or LED, technology.
An LED consists of semiconductor material, part of which is rich in positive charges and part of which is rich in negative charges. And when you pass the current through the material, you generate photons, or units of light. And in principle, this process is 100% efficient, and it generates no heat.
Typical incandescent bulb is very inefficient. Less than 1% of the energy becomes useful light. A lot of it goes into heat, and that's not very useful. Light-emitting diodes were developed in the early 60s, and the first visible ones were developed by Professor Holonyak.
George made the first good yellow LEDs. I had made the first good reds, and Russ made the first good MOCVD crystal growing machinery, and then became a pioneer in growing all kinds of these 3,5 materials by this MOCVD process. George has driven the device from where I was working with it. He pushed it all up the curve. I consider those two men as having done vital pieces of the whole LED puzzle.
I think most people are familiar with LEDs of the type you have in your home appliances or your computer, this type, small LEDs. You can find LEDs today in everything from tail lights to white light, which has great promise for the future.
If you look at the worldwide market for lighting products, the amount of energy consumed in lighting is incredibly large. If we can convert some large fraction of the lighting products to light-emitting diodes, we'll save enough energy over the next few years to basically save billions of gallons of oil.
The foundations laid by Holonyak, Crawford, and Dupuy may make the 21st century the era of LED.
We were going to develop silicon carbide as an advanced semiconductor material and then exploit its properties to make various optoelectronic and electronic devices and sell those devices into what we knew then were 3 or 4 very large markets.
Calvin Carter sees this opportunity to become part of the exploding semiconductor industry.
We were very young. The other founders were a little younger than I, but we were all very young at the time, and we say we were too stupid to realize that we probably couldn't do this. When we started Cree, I was hoping that we would be able to grow an industry, a new industry that would make a difference in the economy of the world.
Carter's advanced technologies raise the level of perfection of silicon carbide. Today, it serves as an excellent foundation or substrate and has helped to revolutionize the lighting and power industries. The 4th hardest known material, silicon carbide is used as a grinding tool and is now even being manufactured as a gemstone called moissanite.
If I recall, one of the guys took a piece of green silicon carbide to a jeweler, and they said, you know, if this were clear, it would look like a diamond. And I think that sparked his interest in thinking, well, maybe silicon carbide would be a great gemstone material.
Through innovation and risk-taking, Calvin Carter and colleagues continue to advance techniques which impact the world in both useful and beautiful ways.
My thought processes are primarily visual, and there are a lot of images in my mind as I think about the work that I'm doing. Usually the images that I start with are very, very far from the ones I end up with. The process in between is anything but smooth.
Carver Mead has spent a career seeing as far as the eye can see and also envisioning what the eye cannot see. A creator of endless firsts, each Mead invention is conceived based on the underpinnings of physics.
In the late 60s, people were all saying that transistors couldn't be any smaller than about 10 microns. And I looked at the basic physics, and it looked to me like they were off by a factor of 100. And it didn't make any sense to me. And when people are saying things that don't make any sense to me, I work on them until I can figure out what's really true about them.
And as the world universally adopted the digital technology that he foresaw in the 60s, Mead turned his curiosity and design acumen to how machines could mimic functions of the human mind.
The evolution of human understanding has many aspects. Science and technology are two of them that are important. But it is a very fascinating and marvelous process. I get into things because I run across something that fascinates me so much I can't not do it.
I love music, and for acoustics work, we got into design of auditoriums, concert halls. We didn't know much about it, and so I decided to make a big research project out of this.
Leo Baranik's dedication to the art and science of acoustics spans more than 6 decades and touches some of our nation's most important historical moments.
The Electroacoustics Laboratory job was to improve communications in combat vehicles.
Post-World War II was the beginning of Baranik's expansion into a diverse spectrum of acoustical projects.
A job came in to MIT from the United Nations architects, asking them if they could do acoustical consulting on the United Nations buildings. It turns out that the job was so big that we decided to form a partnership, and within about 5 years we had about 75 to 100 people working for us and doing buildings all over the United States and eventually all over the world. And so we got to build the first piece of the internet, the ARPANET. And it turned out that it was really our invention.
President Nixon today gave up those Watergate tapes. Fred Graham covered the story.
I would say the Watergate thing was more decisive. They were, of course, concerned about these missing minutes on the tapes that in Nixon's time. And the question was, could we somehow dig out of the tape what was really been said there? It turned out we could not. And the next question was, did the secretary erase those things? And we concluded she was not, that the erasures were done by an amateur and not by somebody who knew how to use the equipment.
With a career spanning 6 decades and countless areas of influence, Leo Beranek remains passionate about acoustics.
One takes pride in being able to do something that's useful, and that is why I stay in the field.
The kind of work that I do represents the sort of fundamental measurement and understanding of chemistry that chemists use in terms of trying to understand how to do things better.
John Brauman's exploration of chemical reactions often finds him looking at molecules in a vacuum.
Molecules have structures, and the structures can be modified, and their chemical reactivity depends on the structure. And what we've tried to do is to separate those two factors.
His insight advanced scientific knowledge by demonstrating the differences in chemical reactivity when molecules are found in a solvent and when such a medium is absent.
The science of chemistry is not completely empirical in the sense of just remembering that something is good and something else is bad, but understanding why something is good so that if you want to do something new, you have a reasonably good idea of how to think about a problem that hasn't been done before.
In a research career spent entirely at Stanford University, Brauman also gives time and focus to his students.
One of the things I think that everybody in my business really gets a huge amount of pleasure from is the graduate students with whom one works. I had a great mentor as a graduate student, and I've tried to emulate him as much as I can in terms of allowing students to develop in their own way, because often different students will do better at something than another.
When I started my graduate work in the early 40s, I read some papers by Hermann Muller, who later got the Nobel Prize in genetics, who pointed out what a deep mystery the gene was at that time. From that point on, I really thought about genes and still am thinking about them.
Evelyn Witkin pioneered the study of biology's response to DNA damage. Her landmark work in DNA repair has played a vital role in biochemical research.
I found that one could not understand how mutations happen in E. coli without understanding what ultraviolet light does to DNA. The particular biochemical nature of the damage was demonstrated by others, and what happens in the DNA of bacteria exposed to ultraviolet light is that two of the building blocks that are next to each other become fused, and the effect is something like a snag in a zipper.
Witkin's investigations into how the cell deals with the snags in this zipper led to her landmark work on the SOS hypothesis.
By the early 70s, in conjunction with Miroslav Rodman, together we proposed that ultraviolet light produces DNA damage which generates a signal that tells a number of genes in the E. coli genome to turn on.
Witkin's career may never have been if it weren't for her courageous stance as a young civil rights activist.
I could not graduate with my class, and I decided to go to Columbia. I have to say that my having gone to Columbia was the greatest blessing because it was Columbia that had the Cold Spring Harbor connection.
The underpinning of biomedical success is
understanding how individual proteins in a cell carry out their task.
James Darnell's pioneering efforts in RNA processing and cell signaling has shaped molecular cell biology and has focused the research of his colleagues and students for decades.
My colleagues and I realized that we had found a new fundamental step in molecular carpentry, cutting apart a longer molecule in order to get the good part out of the center, the shorter molecule. That was the first discovery of RNA processing. We were interested in how the signals from outside the cell could be interpreted inside the cell in molecular terms in order to redirect some important aspect of cell function. We were able to track that down and find the nuclear protein molecules that are in charge of regulating genes. And the purification of that led to this pathway, which has the acronym STAT.
James Darnell's insights and talent continue to improve our efforts to understand and treat disease.
And so the study of these pathways, which are incorrectly acting during cancer, will give us a chance to, I hope, get the drug houses headed in the right direction to find good anti-cancer therapy based on good scientific knowledge.
The work of James Glynn proves that mathematics is indeed the language of science. His research shaped different and distinct branches of the field, and his collaboration with Arthur Jaffe led to the invention of tools that are now standard in quantum field theory.
We listened to the physicists, and instead of trying to invent something that was totally new because we thought they were nutty, we tried to invent something that supported their ideas because we thought they were profoundly right but incomplete.
Glimm's hallmark contributions to shockwave theory, where mathematical models are developed to explain such natural phenomena as earthquakes, volcanic eruptions, and wildfires, are recognized worldwide.
The computation combined with the mathematics combined with the physics, that's really what is, at the present time, is what's driving my inquiry in science. And this is a very profound development to which many people are contributing. And it will absolutely revolutionize all of society.
Today, Glimm has established a Center of Applied Mathematics at Stony Brook and is also director of the Center of Data Intensive Computing at Brookhaven National Laboratory.
Many people can participate and do really deep things in science that they would not be possible before the computer existed. In a way, I think we all have become or have the capability of being Renaissance scientists.
Scientific acumen applied with art in the cause of freedom is how colleagues describe Richard Garwin and his intellectual pursuits conducted for more than 50 years of service to our nation and to science. As a student of noted physicist Enrico Fermi, Garwin began his career in the burgeoning world of nuclear physics.
I was at Los Alamos in the summers, beginning in 1950. So in the beginning, the first week or so, I learned all about fission bombs, read all of the secret progress reports from the various groups during the war. And of course, when you learn something new, then you immediately have ideas which are different from the ones that other people had had. Probably the most fundamental work I did was with Leon Lederman and Marcel Weinrich.
It was at Columbia University where this team of three shattered the long-held concept of conservation of parity, where mirror images should behave in identical ways.
One Friday evening, Leon Lederman and I built an experiment at the Columbia cyclotron using, of course, techniques and instruments that we had long used. And within those few hours, we showed an enormous result, a very big effect, a 2-to-1 ratio in numbers of electrons backwards versus forwards.
From 1952 to 1993, Garwin served as researcher and ultimately fellow at IBM, where his ingenuity led to more than 40 patents that made their way into everyday lives. Garwin applied his brand of insight on matters ranging from national security to arms control to healthcare when called upon by presidents and the government.
I tell it the way it is, and I hope that people will make the right decisions.
Jason Morgan's commitment and passion for data gave science a new unifying look at our planet, the theory of plate tectonics.
Well, I think until the 60s, there was what's called fixist mode, and that things went up and down, but there was no large horizontal motions, that all this new information coming from the oceans just didn't fit the earlier models of how mountains were built and sediments were laid and everything that geology tried to address.
Morgan's pioneering idea that science could predict the spreading of the planet's crustal plates provides a new framework for an understanding of our geologic wonders. Other Earth phenomena took shape by Morgan's analysis into our planet's active interior.
The one idea that I like the most is the idea of the mantle hotspots. I had remembered an earlier paper talking about Hawaii moving over a fixed source, and I said, well, this could be stuff from deep in the mantle coming up in a narrow column. And so you can have ideas like this, and then in order for it to be science, you have to have evidence that proves it. I think the main thing that you can teach students is an appreciation of the data.
Jason Morgan, theorist and teacher, continues to search for evidence of our planet's tectonic activity.
I think people are interested in understanding the universe. When Einstein developed a better theory of gravity than Newton, people were enormously interested. When the Hubble Space Telescope makes discoveries about distant galaxies, people are very interested. Understanding elementary particle physics is part of the quest of trying to understand the universe.
Few scientists have contributed more to our grasp of the universe than Edward Witten. He is a world leader in string theory, an attempt by physicists to describe the forces of nature in one unified way.
The general idea is that all the different elementary particles, quarks, electrons, neutrinos, photons, and so on, are interpreted as different states of a single vibrating string. Different forms of oscillation of the string represent different particles. So, for example, if you have a piano or violin string, it can oscillate at many different frequencies, and that's responsible for the richness of music. And in the case of this kind of string, the different strings give you the different elementary particles.
Edward Witten has inspired the work of whole communities of physicists and mathematicians.
It wasn't part of any plan, but it just turned out that the physics I knew, first of all, could sometimes be illuminated by mathematical insights, and secondly, could sometimes be used to predict or discover things that the mathematicians hadn't known.
Because of Edward Witten's leadership in advancing a broad range of theoretical physics, our comprehension of the universe continues to expand.